Okay, now how do we actually break these bonds between the atoms in a molecule? So we just said that we need energy to break those bonds, but like physically, how does that actually happen? Now, it is not for certain how it happens, okay? But there is a theory on how it happens. So what a theory is that it is a hypothesis that has been tested and found to be accurate. Hypothesis is a statement. So I'll explain it just now, or in terms of this context. But and then they test the hypothesis and see if it is accurate. Now, one way in which they can test it is by making predictions. Like, if this is true, we can expect to find this and this and this and this. And if you do find this and this and this and this, then you have reason to believe the hypothesis, and it eventually becomes a scientific theory. It is one way of explaining. So, for example, Newton had a theory. He saw whatever goes up must come down. So Newton's theory was that large objects, or all objects, attract one another relative to their mass and the distance between them, and inversely related to the distance between them. That we did in, what is it called? In mechanics. And he did his formula, and with that formula he was able to make predictions and plot with that same formula, why does the earth rotate around the sun? Why is it that the earth don't just move in a straight line, but it actually circles the sun? It's because the earth is moving, but the sun is attracting it. So as it's moving, it's making a curve around the sun. And so that was his prediction, and it was fairly accurate. But then they noticed that the type of shape he should make is a circle, ellipse, around the sun, but it doesn't make a perfect ellipse. It makes an ellipse, and I can't remember if it's Earth or if it's other planets that do that, but kind of it does this ellipse, but the ellipse doesn't come back to where it started. It goes away a little bit, so it forms this type of flower around the sun. Okay, so there was a flaw in his theory that large objects attract one another and is constant, and Einstein was the one that eventually discovered what the flaw was, and Einstein's theory is now called the theory of relativity. And what Einstein realized is that space, in fact, is curved around large objects. So, for example, and this has got nothing to do with this, but it's very interesting. Why do large objects attract other objects? Like, why? Like, what is the reason? Why does there exist a force? And his explanation is best to understand it in the sense of, if you were to take a trampoline and you were to stand on the trampoline, and someone places a ball somewhere on the surface of that trampoline, what will happen to that ball? It's going to roll down towards you. There's an attraction towards you because the surface that you are standing on is now curved because of you. Now, let's, for example, take a small baby, and we put the baby on there as well. It will still have a little bit of curve, but now it won't be so dented. So you can put a ball on and we'll move slower towards it. But let's now put a very large person on there, and the curve would be very deep, and so you put something in and it will have a very strong pull towards it. So that's the idea of space itself, and the way that he ended up proving it was by showing that if space is curved, it means that if you shoot something straight at a large object, it should actually go around the object, okay, at a very large object, because space is curved, so it won't go straight. So the only way they could do that, the biggest thing that he could do that to show it, was the sun. And how will you shoot something past the sun and see it curve? Well, the only way they could do it is by looking at stars, because stars shoot photons. And they saw that stars that were behind the sun, so stars that's actually, the sun is between us and these stars, and yet we can see those stars. And that is because the star curves around the sun. And they see it during a solar eclipse. So it was a magnificent experiment. But yeah, so that for example was a theory, examples of theories. There was a theory, it worked, it was able to explain, but it weren't necessarily the exact truth. Like, it's not exactly, but that is the best theory to explain things. And still someone else comes and they have a better theory, or they expand on your theory on why it's true. And now, this is now the theory of relativity. That space curves relative to the size or the mass of an object. Okay. This is going to be a theory on because we can't see it. No one has ever observed. These things are too small to actually see. So we have to theorize on why things happen. And one of the best theories for now on how do reactions actually happen, how do the bonds between atoms actually break and form new bonds, is called collision theory. We know that there's energy being released when a reaction happens, or energy needed, which means we know that the molecules themselves contain potential. They need energy in order to bind. So we know that if we want to break that energy, we need to add some energy. And how do we add that energy? So the best explanation would actually be to say, well, what type of energy could actually cause this break? And the idea that they had, or the theory prevailing, is kinetic energy. That when we actually have a molecule like this one bumping into another molecule like that one, if they could bump one another hard enough, they might just break the bond. Okay? And that would be the theory of the collision theory, is that molecules collide with one another with sufficient kinetic energy to break the potential energy bond. Does that make sense? Okay? So if that does happen, it's called successful collision, a successful collision. So in a successful collision, I'm definitely spelling that wrong. That looks worse. Okay, but it doesn't matter. In a successful collision, we will have that the potential energy, the total potential energy of these two molecules will be less than the total kinetic energy of those two. Let me take that. Do you understand that? In other words, if we take the amount of energy that they have because they are traveling with the amount of energy that they have because they're holding on to one another, or to their atoms, okay, then we find that the amount of energy that they have when they travel is more than the potential energy. Okay, so for example, I'm going to make a fool of myself. I'm trying to think of an example there. Okay, does that make sense? Okay. Now, not all the molecules in a substance. If I have a container with hydrogen and a container with nitrogen, and I now mix them into one container where I want them to react, not every molecule has the same amount of kinetic energy. Different molecules are traveling at different velocities. Okay, so molecules do definitely move around. Okay, so molecules move around, but they don't all have the same kinetic energy. For example, the energy for the molecules on the surface might be more than the energy inside because they have more space to move. They are maybe exposed to more heat or whatever. But if I now go and look at another type, what is this called? Boltzmann? The Maxwell-Boltzmann energy diagram is also an energy diagram, but instead of having energy on the vertical axis, energy is actually on the horizontal axis. So this is the amount of kinetic energy. This is the amount of kinetic energy. Then what we do is we take a percentage. So instead of talking about 100%, I'm rather going to talk about 1. 1 would be 100%. Okay? And we take the all of the how am I going to say this? We're going to have a graph here. So let me first draw a graph and then I'll explain the graph. If I were to paint the area under the graph, the total area under the graph will be 100%. Do you understand? So I'm not looking at the height. I'm not reading off any values on the y-axis. I'm not reading off values on the y-axis. Okay? The values on the y-axis represents frequency. Frequency. That would tell me how many molecules have that amount of energy. But if I look at any value, so let's say that is 10, whatever 10 is, 10 joules or whatever, I'm not using real values. If I ask how many molecules have an amount of 10 energy, well, you've got billions and billions and billions of molecules in a short space. How will you count how many has 10 joules? Okay, it would be impossible. Rather, what we would do is we would ask how many has less than 10 energy. In other words, we'll look at the area underneath. Okay, the area underneath will tell me what percentage of observations have that much energy. Does that make sense? So you will notice this is a type of in maths we do histograms. A histogram looks like this. And these bars represent the frequency in this interval, the frequency in that interval, the frequency in that interval. Now what this is, it's a histogram, but the intervals are just very small. So it's almost like the interval is so small that it ends up making a smooth curve. Do you understand? So these are actually lines going up, but I can't, like it's intervals so small that we only draw the top parts of that interval, and when we draw the top part of that interval, we end up making a smooth curve. Do you understand? So in the end, that's what the Maxwell Boltzmann diagram is all about. And in this diagram, the area under the graph will represent the amount of, or the percentage of molecules that have energy that's less than that. Or for example, so this is kinetic energy. For a successful collision, I need my potential energy to equal my kinetic energy, at least. Okay, so at some point here, this is the amount of energy that I need. What do we call the amount of energy that I need to have a reaction start occurring? We did it in the previous topic. Activated complex. So this is the activated complex. As soon as the kinetic energy is equal to the activated complex, then reaction starts happening. Does that make sense? Okay, so all of the molecules that have enough energy are represented by this part of the graph. Okay, so this represents the percentage of molecules that have enough energy to have successful collisions. Okay, now what happens if we add a catalyst? Yeah, the activated complex. So look what happens now when the activated complex is less. What happens to the percentage of, so remember, everything more than the activated complex represents the successful collisions. So what do you notice about the successful collisions? There's more successful collisions. You see how this works? Okay. What will happen if we include, and I should have actually done this, sorry. What will happen if I add heat into a system? If I increase the temperature of the reaction?
The products form faster?
We're talking about energy. What am I doing if I am introducing heat into a system or into a reaction? What am I doing with the kinetic energy of the molecules?
Increasing it.
You're increasing it. So when I do that, I'm increasing the kinetic energy for every molecule in that system. So this is what will happen. This whole graph will shift, because every molecule that used to be here will now move a little bit there. So this whole graph will now move up a little bit. Did the activated complex move? No. The activated complex is how much energy I need for the bonds to break. I still need the same amount of energy. It's just now, so here is my activated complex, the original one. Okay, so let's assume we don't have the activated complex moves when we add a catalyst. If I increase the temperature, my activated complex is still the same, so this is still the activated complex, but now look at the amount of area under the graph. Is it more or less than the green? More than the green. So the number of successful collisions has increased. So let's quickly say they're going to ask us questions like, what effect will a catalyst have on the energy? Okay, catalyst will answer reduces the activated complex, which in turn increases the number of successful collisions, because a greater percentage of molecules will have sufficient energy. Does that make sense? Because you've now reduced the condition. Okay, it's like making the pass mark from 50 to 30%. More people are going to pass because you've reduced the standard. You reduced what's needed. Now, alternatively, what you could do is you could give them more education. As an example, you could add heat into the system. You could make a penalty for failing or something like that. So there's a greater motivation to be successful. Okay, so you have more successes without actually changing the pass mark. So in that sense, adding temperature to a system will increase the average kinetic energy. Do you see? So the average kinetic energy has increased, and therefore a greater percentage of the molecules will have sufficient energy to have successful collisions. You understand how I'm starting to phrase this? But guys, go now home and revise this and do it in your own words. Explain it to yourself so that when they ask you, we don't want a verbal word-for-word explanation from the textbook. We want to see that you actually understand what does change in temperature do. So the question is, what effect does pressure have? So again, would my activated complex change? If there's more pressure, do I need, is the amount of energy that I need to go from reactants to products still the same? Yeah. That only changes with adding a catalyst. Okay, so my activated complex stays the same. So increasing pressure means that the space where molecules can now move is less. So the chances that two molecules now miss each other, they've got enough kinetic energy, but they still have to hit each other. The chances when there's less space of two actually hitting each other is actually more, the chances of them hitting each other. So the probability of successful collisions is more because, and this is actually probability. What we read off here, frequency is probability. Frequency, it's just frequency divided by total. So in other words, your probability is higher. So I think, I think what will happen is that your probability will be higher. So it will look like this, but I think it might it might go higher like that. Maybe not, but it will definitely affect the shape of the graph. It wouldn't necessarily increase the average because it's not changing the kinetic energy. You're not increasing the kinetic energy when you increase the pressure. Okay, you're actually increasing the probability of collisions. So it will affect the shape of the graph. You know what I think it will do? I think it will do this. So let's do that. It will affect the shape in this direction. It will do. So now you can see it's kind of a bell shaped. It's not necessarily a bell shape. It can take various shapes depending on the reaction and things like that. But I think what pressure will do is it will do something like that. It would move the shape so that the bulge here. So here you can see here's the activated complex, and now we've got all these additional extra collisions happening because I've decreased the so it didn't necessarily change the average kinetic energy because the average might still be the same because there's outliers here at the bottom. There's still a few that have too little energy. Even with collisions, they don't have successful collisions. Okay, make sense? Any other questions? Okay, let me just see that I didn't leave out something. So there was one question which had this in the exam. It was a multiple choice. The Maxwell-Boltzmann energy distribution curve below shows the number of particles as a function of their kinetic energy for a reaction at 4 different temperatures. The minimum kinetic energy needed for effective collisions to take place is E. That's the activated complex. The minimum amount of, so this is the activated complex. Now, which one of the curves represent the reaction that takes place at the highest temperature? So which one here actually represents the reaction that takes place at the highest temperature? 1, 2, 3, or 4? 4, because the area that it has that has the most successful collisions would be represented by that. Okay, so it's not about the height of this curve. The height of this curve this just shows that there's more. That is actually called the modal kinetic energy. It's a kinetic energy that we observe most. Remember chemistry? The modal. So this is the kinetic energy that we observe most for 1. This is the kinetic energy we observe most for 2. So for 4, this energy is the modal kinetic, and it's the energy that we observe most. And the one thing that all these 4 have in common is that if I were to use paint to paint that area under the graph, I would use the exact same amount of paint to paint each of them. The area under the graph for each of them must be the same. And the standard is it's equal to 1 area. It doesn't matter what you use as 1, but their area represents 100% of area. So this one's area is the same as that one's area, but it's stretched out rather than squeezed in. Okay, and this one will have a bigger percentage of his area will actually be on the successful collision side. So this will be answer D. Okay.